So, just briefly, ways you can stay in touch with the Society. Obviously, you can follow our work online at our website, and you can also keep up to date with what we're doing on our social media channels. The information is there on your screen, and you'll get all of that contact information on our website as well. So briefly, before we move on to the main business of the evening, just like to give you a quick overview of what's coming up for us throughout the rest of the year. Our next full monthly meeting will be on Friday, the 1st of July, and that, of course, will be an in-person and online meeting at our usual meeting place, the Augustinian Hall here in Edinburgh. And that will be a members' evening, similar to one we held a few months ago, which I think people found very enjoyable. Our imaging and observing group will be meeting on Wednesday, the 6th of July. That will be for members only, as normal. And then on Friday, the 15th of July, we'll have an online meeting again with a presentation on the Icarus Observatory, First Light Optics Community Project from Grant at First Light Optics. And that again will be virtual on Zoom and on YouTube. After that, we'll take our traditional summer break from mid-July until about early September. Of course, with the easing of COVID restrictions, now the Edinburgh International Festival is back in full swing this year. So many of the venues in the city, including our own traditional meeting place of the Augustinian Hall, will be quite busy. We expect it'll actually be in use on the first Friday of September, which will be the 2nd. So it's likely that we'll be back on Friday, the 9th of September. That's the 2nd Friday of the month, when we will kick off our autumn program of events. And you can see on screen there some of the things we're hoping to bring you, including the ground effects of space weather, space art, and the origins of life on Earth and other planets. So, Peter, I think your sound might be on actually for the moment. Without any further delay, I'd like to welcome our main guest speaker for this evening. Natalie Starkey is a geologist and cosmochemist. Following her PhD at Edinburgh University, where she studied the geochemistry of Arctic volcanoes, Natalie's postdoctoral work was at the Open University, where she moved her interest to focus on comets and asteroid samples. And it was around this time that she had a chance to analyze samples returned from the NASA Stardust mission and the JAXA Hayabusa space mission. Natalie received a British Science Association Media Fellowship in 2013, and the same year she became a BBC Expert Woman. She regularly appears on radio and television internationally, as well as being a science host on Neil deGrasse Tyson's popular Star Talk Radio. She's written numerous publications, including Fire and Ice, Volcanoes in the Solar System, which we're about to hear a little more of very, very shortly, Catching Stardust, Comets and Asteroids and the Birth of the Solar System, as well as numerous publications and articles in publications like The Guardian, The New Scientist, All About Space, and Sky at Night magazine. So I'll stop sharing my screen, and I'll now turn the meeting over to Natalie for her presentation. And after she finishes, we'll have an opportunity for questions and answers. So Natalie, over to you.
Lovely, thank you. I'll just share my presentation, which is usually a bit slow on Zoom, so hopefully it'll catch up in a minute. Right. Hopefully you have got the presenting view, not good. I think we're good to go then. Brilliant. Well, thank you all for coming. I believe the weather in Edinburgh is not as hot as it is down in East Anglia today. We've had literally 34 degrees Celsius today, and it's still 29 outside. So I've got my fan on. I'm going to talk about volcanoes, which I guess is quite good for today, considering it's very hot. But I'm happy to move on to the ice volcanoes later on in my talk, and hopefully that will cool me down a bit. So let's get started. A little bit about me. Well, Sean introduced me a little bit, but I'll just go in a bit more detail about my background. So I studied for a master's in geological sciences at Durham University initially. And actually my work started out on a volcano in the Caribbean, in Montserrat, where I did a lot of field work and I got to analyze samples, and I really caught the bug for research at this point. So I went on to Edinburgh to look at volcanoes in the Arctic. So I was looking at volcanoes in Baffin Island and West Greenland, and also the north of Scotland, in a big volcanic complex that's all related back to 60 million years ago. Did a lot of geochemistry, analysing those samples to understand really more about the Earth. And it was the first time I'd really kind of thought, okay, so we're using volcanoes to understand not just about that volcano, but about how the Earth itself formed, where, you know, that volcano came from and what is happening inside the Earth to produce what we see at the surface in this huge outpouring of lava, which happened 60 million years ago when the continent started to divide up there. Now, from there, I went to the Open University down in Milton Keynes, and I did my postdoctoral work for about 7 years on comets and asteroids. Now, it might seem like a bit of a leap to go from studying volcanoes on Earth to comets and asteroids, but actually the link is that these are all rocks, and it sounds very simple, but I'm a geologist, and actually I like to study rocks. It all really doesn't matter where they come from, to be quite honest with you. I can do the same geochemistry on all of these samples, and we're just trying to answer different questions. So in terms of the comets and asteroids, I was trying to understand literally how the solar system formed, because these were the very first objects to have formed in our solar system before the planets. So they can tell us a lot about where everything came from. And that led to my first book, which Sean mentioned, which is Catching Stardust. And then I really love writing, and I thought I really want to write a second book and actually want to go back to where I started and look at volcanoes. But my publisher told me, weirdly, he was like, we're never going to sell a book on volcanoes, you're going to have to broaden it. So he said, can you look at space volcanoes? And I thought, well, that's definitely something really exciting. I don't know anything about space volcanoes. So this began my research for the second book, which was amazing. I learned so much, and I was able to kind of apply all my spacey and geological knowledge to that and produce Fire and Ice. So apart from that, I'm back at the Open University now. I spent a few years out in California doing science communication. I came back to the OU and I worked doing science communication for them, and I'm moving on to actually the Royal Society of Chemistry at the end of the summer to be their science media producer soon. So basically science communication, as long as I can talk about science or write about science, then I'm happy. So Catching Stardust, the first book, I'd love to come back and talk to you about this book. It actually came out in 2018, but so it feels kind of a while ago now, but a lot of the science in this is 100% relevant still. Towards the end of the book, I start to look at the future of comets and asteroids. So the beginning starts with like looking back in the past, how we've used comets and asteroids to understand a lot about our history of our planet. And then it goes through some of the main missions that have gone to investigate these objects in space. And then the end of the book is looking to the future. You know, how might we protect our planet from impacts from comets and asteroids? And then also how we might mine them in the future, which has become such a big topic recently. And obviously it is something that's going to happen. It just depends when. And so that's a whole huge topic, which, I mean, there's been entire books written on that in itself. But yeah, I cover kind of everything I think there is to do with these fascinating objects. So let's get back to the volcano. So I'm not sure how many of you are interested in geology, but hopefully if you're not, by the end of this talk, you will at least be a little bit interested. And I can share some of my passion for why I got excited about studying geology from the start. My inspiration was back at school in the 1980s and 1990s. I learned about these two amazing scientists, Katja and Montserrat, who studied volcanoes. And it wasn't just that they studied them, you know, they were scientists, but they, you know, were photographing and following these events live as it happened. And I was just amazed by this story, that these two people would hear about an eruption happening on the other side of the world, you know, before the days of social media, where, you know, it would take a little while for us to find out about these events. They jump on a plane and want to be there and want to be right next to that erupting volcano to capture so much amazing information. Now, it's quite exciting because without these two people, we wouldn't have the amount of knowledge back in the 1980s and 90s that we had. We wouldn't have had without them, because no one got this close to volcanoes. Now, you could say that they were slightly reckless in some ways, that they just felt like they needed to get close and document these events happening. And ultimately, obviously, they, as many of you probably will be aware, they ultimately lost their lives on Mount Unzen in Japan in 1991. They thought they were in a safe location on a ridge that was close to the erupting volcano, but you'll see in the middle photo at the bottom there, one of these huge flows came down the side of the mountain, and these are pyroclastic flows, and Some of them are less dense than others. They're pretty unpredictable. They can be quite dense, but some of them are less dense, and they can kind of stick to a valley or they can not stick to a valley. And in the case that they were involved in, the flow kind of inundated the hillside around the valley where they were documenting the volcano. Now, they weren't the only ones to die in this incident. There was a very famous geologist called Harry Glicken involved in it as well. So, you know, it's part of what is studying volcanoes. It is inherently dangerous. And I guess what I think about is studying space volcanoes. At the moment, we do it all remotely, but you know, one day we're going to want to go out and study these things in person. And we're just mixing, you know, two really dangerous hobbies there, being an astronaut and being a volcanologist. But as we start to understand volcanoes more, and thanks to these two, we do understand them a lot more, we can actually go out there and be a bit safer, because we understand a bit more about when volcanoes are going to erupt and then how they're going to behave based on what they've done previously. Now, I haven't seen this movie yet. I love movies, and I like to kind of bring these in whenever I can. There's this new movie out called Fire of Love, which is about their lives documenting volcanoes. It's done really well so far in all the festivals, and I can't wait to see it. I don't know when it's going to be out on kind of Amazon and all those channels, but I think it will be worth watching, and I think it will be really interesting. I know one of the people that consulted for it to make sure the science was accurate. So let's go back to the destructive power of volcanoes. So many of us will have learned about Vesuvius, AD 79, as one of those really classic volcanic eruptions that I think most of us will have learned about in school. And I don't know if any of you have been lucky enough to go out to Pompeii and visit the archaeological ruins, but I went, I think I was about 15 when I went, really excited about volcanoes at the time, and amazed that this whole site existed, that, you know, these people had literally been frozen in time from this volcanic eruption. And the important thing to note here is that this happened because we didn't understand volcanoes very well. Now, in the preceding years before this eruption, this volcano gave many signs it was about to have a big eruption. There were many earthquakes leading up to this eruption, and there were smaller eruptions that happened beforehand. There were lots of signs that, yes, it was about to go off big time, but we didn't understand those signs at the time. Yeah, some people were documenting it, and we have, you know, those documents written down in history. But no one took that, you know, step to go, oh, hold on a minute, I think we might not be safe sitting on the flanks of this volcano, because, you know, they didn't know what was going to come. Now, the thing about ash, I think when you look at these ash clouds, is that it kind of just looks like smoke, and you think, oh, it's just ash, you know, whatever. Why is that so dangerous? But the top right-hand picture shows you ash under a microscope. And the thing about it is that it's extremely sharp material. So you've got to think of ash as exploded rock, and it's shards of glass, essentially. So if you take molten rock and you explode it out of a volcano and you cool it really quickly, you're going to create shards of glass, just like how we create glass for our windows. You have to cool and quench glass really quickly, or silica, sorry, you have to cool silica really quickly. Now, the rock that comes out of volcanoes is silica rich, and sure enough, you create glass when it comes out. So the issue with ash is not just that these flows are incredibly hot. They can be over 1,000 degrees Celsius. They can travel at 700 miles per hour. But if you were to breathe it in, even if it was cool, you're going to be breathing in glass shards. And even villages that were, you know, quite far from the volcano and weren't inundated with the hot pyroclastic flows itself, they had a lot of ash fall. And it could take, you know, days or weeks for people to die just from breathing in cold ash that was just in the air. So we've got to understand that volcanoes are extremely dangerous, and, you know, we can't stress that enough. But unfortunately, this ash, or fortunately, depending how you want to look at it, is really fertile stuff. If you add it into land and you work it into soil, it's got a really good property of retaining moisture in the soil, and it adds lots of nutrients that are required for farming. So we find that in a lot of poorer communities, they live really close to volcanoes, and they probably know how dangerous those volcanoes are, but ultimately they kind of think, well, it doesn't erupt very often, and we've got to live, we've got to farm, we've got to make food, and so this is a really great fertile place to do it. So there's this very awkward relationship, which I talk about in the book quite a lot, where we need to live close to volcanoes, particular communities need to, but we also need scientists to explain to these communities and kind of forecast these eruptions to help them move away when it's absolutely necessary. Now, I call it the Pompeii of the Caribbean, but luckily it had a slightly different outcome. So this is the island of Montserrat it's just near Antigua in the Caribbean, and it's a small British overseas territory. The island's about 10 kilometers north to south by about, I don't know, 4 or 5 kilometers east to west. It's a beautiful place. I do encourage anyone to go and visit it. Despite it having an active volcano, most of the island is relatively safe. The island sits on the southern portion, and it's called the Soufriere Hills. Now, in 1995, a really huge eruption started on the volcano. Now, you'll see that Plymouth here is the capital, or was the capital of Montserrat at the time. And the scientists, in this case, because they've been studying the volcano for quite a few years, they knew that it was about to erupt. Now, they didn't know that it was going to erupt on, say, the 15th of July or whatever, but they knew within a few months there was going to be a really huge eruption at this volcano. Now, the dome that you can see today is extremely unstable, and the same thing had sort of built up previous to this eruption. Now, this dome, or what you might call the volcano peak, you can see how unstable it is. It's got all these boulders sitting on it, and it's literally steaming away. All our fieldwork, which I did out on the volcano here, was done by helicopter. It was very exciting, very James Bond. And we were, taken around the volcano. They were never allowed to stop the engine near the volcano in case, we had to get away really quickly, or the helicopter engine didn't restart again, because we literally would have been stranded. But when you're standing next to that volcano, it's roaring away. The steam escaping from it makes such a noise that I was really shocked about. I had no idea that standing next to this kind of volcano would be that noisy. And the top right image shows you kind of those hot areas. So where you can see that steam escaping, those are really, really hot fumarole vents coming out. So Plymouth was the capital. Now, it was quite a thriving Caribbean town of over 3,000 or 4,000 people living there. There was actually very famous music studios there as well, called Air Studios, run by the Beatles producer, Sir George Martin. And he, had bands coming out throughout the 80s, like all the music I grew up listening to. It was pretty much all recorded out in Montserrat, and it was this kind of paradise of place to record music, because they got to live on this beautiful island and walk around Plymouth. Now, today, as you can see from these images here, Plymouth's completely submerged under ash and boulders. And I think it just shows us that, this is what happens when this volcano collapses. It doesn't just erupt, it does erupt, it has a massive eruption, but this whole dome pretty much collapses down the hillside and just inundates that valley with all that material. Now, luckily, in this case, the scientists managed to forecast that this was going to happen, and they got nearly everybody out. Now, I say they got nearly everybody. Some people refused to actually leave Plymouth because they'd been there their whole lives, and they didn't trust the scientists. They didn't trust that they really had to get out, and that this devastating thing was going to happen. So most of the people did leave. They had to be rehomed to not just other parts of the island, but all over the Caribbean, even into Britain and the US, because the island's not very big. It doesn't have enough places to put all those people. Some people have never returned to the island, in fact. But it's a case that, they got it right this time. And the scientists now have a really good relationship with the people on the island, and, they trust them. And no one will be going back into Plymouth anytime soon in the next, hundreds of years. It's always going to be an exclusion zone for as long as we'll know anyway, because that volcano isn't going anywhere anytime soon. I mentioned that studios. There's another film which I have seen. It's out. I watched it on Amazon, so you can definitely download it. It's called Under the Volcano. It doesn't really cover the eruption itself. It covers up to the stage just before the eruption starts, and up to whatever, a huge tornado that went through, or cyclone, or whatever it's called over there. But it covers the story of those studios and kind of living on that island, and all that exciting music that was happening. I don't know if you like 80s music, those people listening, but I do. I think it's brilliant. So it was all recorded out there. So have a look for that. I highly recommend it. Kind of a documentary movie. So I talked a lot about, the destructive nature of volcanoes, but it's not all bad. And so I do spend a chapter of my book talking about how volcanoes construct new land. Now, one of the most famous examples is Surtsey in Iceland, just off Iceland. when a whole new island was built out of nowhere. So we obviously know that Iceland itself is on the mid-Atlantic ridge, and it is itself built up bigger than the rest of the mid-Atlantic ridge, because there's also a mantle plume lying underneath that bit of Iceland. Now I'm going to come on to what mantle plumes are in just a minute, but it basically built up a big island over time. And the volcanoes in Iceland are related to all those volcanoes that I studied in my PhD, the ones in Baffin Island and West Greenland and Northwest Scotland. Now, Surtsey popped out of the sea out of nowhere in the 1960s, and it's probably going to disappear actually, because it's not big enough to kind of withstand the erosion happening from the ocean. But what scientists have been able to do with Surtsey is study how organisms start to inhabit this new land, and it creates whole new kind of places for people, for animals to live and plants to grow, and we're literally making new land on our planet. This has been studied extensively in Hawaii. Now, there's a huge eruption in 2018. I went to Kilauea volcano literally 1 month before, or was it 2 weeks before that eruption happened, when the lava lake at the volcano emptied and, you know, started creating all these lava flows on the southern portions of the island. So it's amazing how quickly after that happens, organisms find a way to make life again. So there's these really cool plants that are adapted to quite high altitudes on the volcano, and they can literally just make life within these what would seem really inhospitable lava flows. Like there's nothing there, there's no soil to speak of. They just find a crack in some lava flow that's cooled down, and you know, they make life, and they stabilize the slopes, and they allow other animals to come in and live there. So life finds a way really quickly. The red plant is really cool. I didn't know when I went out that the berries that appear on this plant, apparently if you pick one and eat one, you can eat them. You have to make an offering to Pele, the goddess of fire, lightning dance on volcanoes and violence, otherwise bad things will happen. So if you do go to Hawaii, then make sure if you pick one of these to do the right thing. So I wouldn't want anything bad coming to any of you. So I've talked about the volcanoes on Earth quite a lot, but let's move on to thinking of Earth as a planet, because I think this is what happened when I moved on to my postdoc work. I was always thinking about Earth and it's just Earth, it's where we live. I wasn't really in that mindset of like Earth is a planet in space, and there's many of these planets. And so maybe we can study our own planet the way that we study others. So what we need to do is kind of take a satellite view of our own planet, or imagine, for a bit more fun, we're, you know, in an alien spacecraft traveling from a far off land and seeing Earth for the first time. What might we be able to deduce about our planet if we just kind of flew over and orbited around? Well, of course, we'd see volcanoes. Even if we couldn't see life itself on the planet, we'd probably see vegetation, that's for sure, but we might not be able to see animals. But we definitely see these volcanoes. And at any one time, we would almost certainly see a volcano erupting, or some sign that the volcano was hot and emitting some kind of gases into the atmosphere. And this would tell us a lot about that world. It would tell us that Earth was not dead inside. It was warm inside and producing heat that had to escape out into space. And this tells us that world is not dead. So, for example, we look at the moon, we see a surface that is cold and dry and cratered. We know that's a dead planet or moon. We know there's nothing really going on inside, although it's not freezing cold within the moon, it's not warm enough to convect and produce volcanoes at the surface. So if we looked at Earth, we'd know that there was something probably quite exciting going on. And that's the kind of thing we apply to other planets. When we go out, we can do comparative planetology. We look for things that are like what we've seen on Earth, and we can study our own planet using the same methods by satellite. But Earth's a bit weird. This is the problem. Now, we've got a really, really special planet. You might not have noticed, or you may, I hope, have realized we're the only planet that has life so far. That's a bit weird, right? Why? Okay, I honestly think there is life out there somewhere. But so far, we're the only place that we know life exists. So we have one data point. Okay, so what does it take to make life on a planet? Well, there's a few other weird things about Earth. We have liquid water at our surface. We haven't found another world in our solar system that has liquid water at the surface, so without covered by ice or anything like that. And the other really important thing is that we have plate tectonics. Now, that might not be instantly obvious from an alien spacecraft, but once you start studying our planet for any period of time, you realize that the surface of our planet moves around, the portions of the outside of the surface are broken up in a jigsaw puzzle, and they move and jostle around in relation to each other. And this means we have things like subduction zones, where you've got one piece of this plate moving below another, and you create volcanoes like the ones we see in Montserrat, like the Soufriere Hills. And we also have mid-ocean ridges. The pink lines on the top image show where two plates are moving apart from one another. This is why we have the mid-Atlantic ridge where Iceland sits. This is where we create new ocean crust out of the mantle of the Earth, and we're creating new crust all the time, and those two plates are moving apart from each other. Now, mid-ocean ridges are really, really important, and we haven't seen a mid-ocean ridge anywhere else yet because we haven't seen plate tectonics anywhere else. Now, it might be that Europa, a moon of Jupiter, has some kind of sort of icy plate tectonics. It seems like its ice, its outer shell of ice is broken into plates that may move a little bit like the way that our rocky plates move in relation to each other, but we've never seen anything convincingly like Earth. And the really cool thing about mid-ocean ridges is that back in 1977, the Alvin submersible was sent down to the bottom of the Pacific Ocean and found vents of hot mineral-rich fluids pouring out from the mid-ocean floor. Now, that was kind of interesting to start with, but it wasn't unexpected. We knew that there was heat down there because these plates are moving apart and releasing material from the inside of the Earth, which should be hot. But what the scientists found was that these vents were inhabited by previously unknown organisms, and they seemed to thrive in the absence of sunlight. Now, you've got to think these mid-ocean ridge volcanoes down at this depth are like 2 to 4 kilometers depth. There is absolutely no sunlight down here. And everything we know about on the surface of the Earth or within the surface of the oceans, we know about, it requires sunlight. It's either the plants that photosynthesize and make their own food, or we eat the plants, or the animals eat the plants and create food energy that way. So what was completely unexpected is that there's organisms down there that don't require sunlight, which sort of changed our understanding of what might be possible out in space. If organisms don't require sunlight to thrive, then maybe we can look in different environments for life elsewhere in the solar system. So these organisms, they use something called chemosynthesis. So they're basically getting energy from chemical reactions. And actually, some of them are creating, they're basically photosynthesizing from the UV that's given off from the heat and from the energy that comes out from those hot rocks, the radiation that's given out from down at these depths. So these organisms are called extremophiles because at these depths, it's either very cold with high pressures, or it can be very, very hot if you're right next to one of these vents. It's environments that we just don't expect organisms to be able to survive in. So this is the thing, we can now go out into space and go, oh, look, there's this weird moon around Saturn that there's no chance it could have life. But actually, once we consider what's possible on our own planet in these more obscure locations, we can start to go, oh, wait a minute, it might be possible on this weird moon of Saturn because actually life isn't necessarily like we know it on Earth. So I mentioned mantle plumes earlier because they are the kind of third main way that we can make volcanoes on Earth. And we have lots of mantle plumes. So a mantle plume is essentially a hot chimney of rock rising from the very core of our planet. And it rises all the way through the mantle of Earth, and it's kind of hotter and more fluid, and it'll erupt at the surface. And this is why we have Iceland. It's why we have Hawaii. In fact, the whole chain of volcanoes on Hawaii is due to a mantle plume sitting still within the mantle, and the crust of Earth moving over the top because of plate tectonics. So you get this chain of volcanoes, which happens quite often on Earth. Lots of places across the planet are produced by mantle plumes. And obviously Hawaii is the main example. Mauna Kea is a huge volcano. And I like to show this image of it kind of from space so that we can kind of see that it doesn't look like what we consider a classic volcano. So I was, if you're going to draw a volcano, you get a 5-year-old to draw a volcano, it's going to be a conical peak, usually with some snow at the top, with a bit of smoke coming out. And that's what they'll probably draw. Now, this doesn't really look like that, because the kind of volcanoes that mantle plumes produce are extremely wide and flat, but they are extremely high still. Mauna Kea, from the base to its peak, is the biggest volcano on the planet, but most of it's under the sea. It's just extremely, there's so much lava there. Now, if we go out into space and look at volcanoes that might be similar, we come across Olympus Mons in Mars. And this is just one of many large volcanoes on Mars. It actually sits alongside two others within the Tharsis region. And it doesn't look that dissimilar, I think you'll agree, to Mauna Kea. It's flat, it's kind of wide, it's what we call a shield volcano. And they're called this because it looks like a warrior's shield lying on the surface of a planet. And sure enough, Mars's Olympus Mons was produced by a mantle plume. So we may not have plate tectonics on any other world we've gone to visit so far, but what we do have is mantle plumes, and thank goodness we do, because they've given us volcanoes all across the solar system, which we've been able to study in similar ways to the ones that we have on our own planet. So I've mentioned that there obviously are volcanoes out there in the solar system, but we need to understand a bit more about why they're not everywhere and why we get them in the places that we do get them. Now, the key requirement, probably, I think you'll probably expect, is going to be heat. We know volcanoes are hot, and you need to melt rock in order to make what I'm going to call a normal volcano. Now, in Earth, 50% of our heat came from the birth of our planet. So it's called primordial heat, and it's literally been trapped within our planet in the core and the mantle since the Earth formed. And that heat has just been radiating out to space for 4.5 billion years since. But the other half of our heat comes from radioactive decay of elements within our mantle and crust. These are elements that just decay and give off radiation over time. And it's a tiny amount, but actually, because there's so many of these elements, they can produce a huge amount of heat. Now, combined, these two heat sources mean that the center of our planet, or the outer core of our planet, is kept molten, and the mantle of our planet, which is made of solid rock, is able to convect. So often people think of our mantle as a liquid because it moves, but you mustn't really think of it like that. It's actually a solid that can flow, which is kind of always, that's one of the things we always learn very early on in geology, and it's quite hard to get your head around, but it moves because of the pressures and the temperatures it's under. So heat is a key requirement. So we need to think about that when we go out to look in space. Do we have hot worlds out there that might be able to produce volcanoes? So let's go out with the NASA Voyager mission. So the 1970s and 80s was an amazing time for space science. And I think, the Voyager missions were like some of my favorite missions of all time, because of the amount of work they did, the amount of things that they discovered for science. It's just fascinating. They got out there, and the first thing they did was discover that Earth is not the only active planet. And before this, we really didn't know whether that was the case or not, because we looked to our moon, and that's our closest neighbor. That's the one we can see easily, and it's kind of like Earth. It's made from Earth, but it's cold and dry and dead, and nothing's going on the surface. And we kind of expected that everywhere was going to be like that, because once you get past Jupiter, everything's very cold. Why is there going to be volcanoes out there? Now, first of all, Voyager 1 got to Io, which is the moon of Jupiter. And then between the two Voyager craft, they saw 9 volcanic eruptions happening on Io. Now, the surprise, first of all, was that Io was hot because it's a moon of Jupiter, and it's sat, past the asteroid belt. It should be very cold out there. And it's also a really small world. So we expected it to be frozen solid, much like our moon. We just didn't think it could be producing any heat any longer, because it didn't have much heat left over from the birth of the solar system, because it's small. It should have lost all of that heat. And because it's small again, it didn't have much inventory of radioactive elements to produce heat. So it really should have been cold, but it wasn't. It was producing a lot of active volcanoes, and it's actually the most active planetary body in the solar system. And then we got to Enceladus, 1981, and what we were expecting, this is an icy world, we were expecting a heavily cratered world, just like our moon. We thought, sure enough, it's an icy world. It's going to have been impacted by comets and asteroids over the course of 4.5 billion years. It will be completely pockmarked across the surface. But what Voyager discovered was that there were smooth plains across the surface of Enceladus. Now, to a planetary geologist, this is just absolutely fascinating, because if there's a smooth plane, it means that somehow your two assumptions can be that that planetary body is either avoided being impacted over 4.5 billion years, which is impossible, or it's found a way to resurface itself over time, meaning that it's been able to cover over the scars of those impacts, meaning that it's active in some way, which was completely unexpected. Well, Enceladus is only at Saturn, but then we go all the way out to Triton, a moon of Neptune. I think it's 4.5 billion kilometers from the sun. And what they saw there were these dark plumes, or wind streaks as they've called them. You can see them a little bit on the bottom right-hand image. And instantly the scientists were like, hold on a minute, these look like, ash or dust or something streaming out of volcanoes on the surface, but it wasn't really known. But these were icy worlds, right? So we couldn't just call them normal volcanoes, we called them cryovolcanoes because they were made of ice. This completely turned everything on its head. Volcano scientists were a bit confused because we thought we had this idea of what volcanoes should look like and how they should behave, and that they should be made of rock, and they should be molten rock and ash made of rock. And then, Voyager went out there and showed us that, perhaps Earth is the weird one. Perhaps we're the strange planet, and actually ice volcanoes are really, really common out there, not requiring any rock at all, or even high temperatures to speak of. So how to spot an active world? I kind of alluded to this already, and it's the cratering history. Cratering is so important, and I'm sure many of you know about the beautiful cratering across the moon, which we get to see, particularly if you've got even just an amateur telescope. You can see kind of beautiful images like the bottom left, sorry. Now, the cratering on the moon shows us that it's been dead for somewhat 3 billion years. Nothing's been going on there. Those comets and asteroids that have impacted the moon have left their scars, and the moon's not been able to do anything about it. It's not had active volcanoes to cover over those scars. But of course, we know that the mare basalts that we see on the moon, those big dark patches of earlier volcanoes that had, flown on the moon and erupted on the moon and covered over those earlier impact basins. So we know that it was once active. And sure enough, this beautiful picture of Enceladus, you can see a few impact scars, but mostly you've got these smooth plains. And then Venus, okay, we can't see that very easily without radar, but when we do reveal its surface on radar, what looks like rivers running across the surface of this planet is, huge lava flows, and hardly any impact craters in sight, suggesting that this is a very active world. And thank goodness we're going back to study it, I think, with 5 new missions over the next decade. So we're going to be learning a lot more about Venus. So let's get on to some of these fiery worlds and investigate their science in a bit more detail. Obviously, I've mentioned the moon. Obviously, it's beautiful, and I'm sure you've all looked at the moon on numerous occasions with telescopes. And I've always found it absolutely fascinating. As I've mentioned, the mare basalts, originally they were thought to be, oceans. They were thought to be water back in the day because we didn't know any better. We thought, well, they're dark patches. They look like they could be lakes or big bodies of water. But sure enough, we go there and we find out it's dry and these lava flows. And as you can see, they when you look closely at these regions, there's hardly any craters in them, which shows us they are younger than the surrounding areas. So you've got lots of lava having flowed on the moon, and you've got regions like Hadley Rill, where you've got these extremely long lava flows, and it's quite hard to stress how long these are, 120 kilometers long, and they're really wide, 1,500 meters wide in places. And that flowed about 3 billion years ago. These are really long lava flows. They were very fluid, which is kind of weird because we have quite fluid lavas on Earth. You think back to the flows that happened on Hawaii in 2018, but nothing of this length. These are extremely fluid basalts, and they are made of pretty much the same materials that we find in the volcanoes that happened on Hawaii. But it's not all about really fluid stuff. So we know that, the mare basalts are, flowy and they fill these basins. But it was thanks to Apollo astronaut Harrison Smith, who is the only geologist to have been sent to the moon. And I think, you know, therefore the best astronaut to have gone up there. And it was thanks to him that we actually learned about the more fiery eruptive history on the moon. Now, the story goes that Harrison Smith was out on the moon buggy, and they were heading back to the lander because they were running out of oxygen. I think they had about 30 minutes of oxygen left, and then NASA were like, you need to get back, we need you back, otherwise, you know, you're going to run out of oxygen and die. But being a geologist, and I get this, he drove past what he saw as these orange soils, and, you know, everything being slightly grey on the moon. I guess he got a bit excited there was something that wasn't grey, and he would not continue. He said, no, I have to stop and sample this. NASA were getting very angry and said, you need to get back, you're going to run out of oxygen. He said, no, I'm just going to sample it. So he did. He went against orders and stopped and grabbed a bag of these orange soils, and thank goodness he did, because it turned out that these were some of the most exciting samples from the moon, although there are many great samples from there. But they formed, these are glass beads, essentially. When you put them under a microscope, these orange soils are made up of these very small pieces of glass, volcanic glass, which formed in fire fountain eruptions. You might remember back to September last year on La Palma, where we had these amazing fire fountains happening, covering a lot of the island. Now, this is exactly how these kinds of soils form. When you explode high silica-rich lava out of a volcano at very high temperature and cool it in the atmosphere, it kind of forms these glass droplets that come back down. So we know that the moon's history was not just, you know, boring lava flows. It also had these fire fountains happening 3.5 billion years ago. And we really wouldn't have known this without sending an astronaut to the moon. So, you know, I have slightly mixed views about sending people out maybe to Mars and exploring further into the solar system, simply because of the distances involved and people having to be away and it being very dangerous. But I guess it was very dangerous going to the moon back in the 1960s and 70s. But if they hadn't been, we wouldn't have the samples that we have today. We wouldn't know the amount we do about the moon, and therefore the rest of the solar system, because we've been able to extrapolate out from there. So, you know, we've still got tons of Apollo rock left to analyze, thank goodness, because we've got, you know, techniques developing all the time where we can continue to analyze things and improve what we're doing. And without sending scientists out, you know, it's great. You know, most of the Apollo astronauts were fighter pilots, and, you know, they were probably very good at flying and everything, but actually sending scientists is key, isn't it? We've got to have people that are trained to look at the right things and look at those rocks in detail and spot those orange samples. So moving on to Mars, I've mentioned Olympus Mons, and obviously it's formed by a mantle plume along with 3 other large volcanoes in the region. Now, I think many of you will know that if we tried to put Olympus Mons on Earth, it would literally collapse under its own weight. It's 25 kilometers high, and it would simply collapse because we're a larger planet, we have more gravity, and so we wouldn't be able to hold that volcano up that high. So it's been able to grow that large, and it wouldn't be able to do it on Earth, not just because of our increased gravity, but also because that mantle plume has been able to sit in one spot for the whole of its existence, and there's no plate tectonics to move that crust away from it. So whereas in like Hawaii, we create a chain of islands from that one mantle plume, in Mars, we've had that one mantle plume just piling out lava into that one spot for billions of years, creating this huge volcano in one place. So, you know, if that had happened in Hawaii, Mauna Kea, or the original volcano on Honolulu, what's that island called? Completely gone blank. The first island, that would have been completely enormous, and we wouldn't have had a chain of islands after that. But it's not all we have. We've got, again, like on the moon, we've got these huge lava flows, really fluid lava flowing across the moon. What we see with this image on the right is that the lava's kind of carved out a channel across the Martian surface. So again, very similar story to the moon, and another very similar story in terms of we also have very explosive volcanoes. Now, this was actually discovered quite recently. We've got this very old region of Mars called Arabia Patera. And for ages, these features were thought to be craters because, you know, from far away, you probably think, yeah, no, I can believe that's a crater from an impact. You can see impacts around that. They're nice, aren't they? They're nice and rounded and they look very smooth. But actually this huge feature in the middle here doesn't look as smooth. It's a lot more of a complex feature. There's a lot more going on in there. And actually what scientists now think is that this region of Mars experienced some really large supervolcanic eruptions. Now, supervolcanoes, appear in the media quite often, and they probably shouldn't, because we don't have that many supervolcanic eruptions happening. They don't happen very frequently. We hear about Yellowstone in the media very, very often, and the Daily Mail probably like to say it's going to erupt, next year, or it's overdue an eruption, and that's never the case really. The thing about these big supervolcanoes is that they let off steam. So they might have not had a huge eruption for 75,000 years and therefore one's due, but actually because they're complex systems, they let off steam in different ways. And so you can't really forecast when they're going to erupt in that manner, in that, in terms of the frequency. You have to study a lot of other factors. So, I think we're safe from Yellowstone for quite a while. But the thing about supervolcanoes is that they are almost always due to mantle plumes sitting underneath the surface. And, I think it's probably quite likely that on Mars, this is what we're looking at here. So let's have a look. We're going to talk about sizes. Now, for a supervolcano to be a supervolcano, it has to have erupted 1,000 cubic kilometers of material. That's kind of hard to imagine. Now, it could be ash, it could be exploded rock, or it could be literally lava flows, so basalt lava pouring out. Now, if we want to think about explosive stuff, I remember learning about the Mount St. Helens eruption, I think 1980, is that right? I'm just going to grab, I've got some ash here actually from it, 1980, there we go. I don't know if you can see it because my screen's blurred, May 18th, 1980. This eruption was not a supervolcanic eruption. It produced 2.8 cubic kilometers. So it was a very large eruption, but nowhere near 1,000 cubic kilometers. So we can just imagine, the devastation caused here versus what would happen if, Yellowstone were to erupt. Yellowstone hasn't erupted, I think, for 640,000 years. And when it did erupt, it produced the huge caldera that we now see there. So it would be very large. One of the largest eruptions on Earth was Lake Toba. It's quite hard to kind of show the extent of this lake because it's so large. I think Lake Toba in the right-hand image is actually only a small part of that entire lake, as far as I can tell. But that whole caldera was formed during 4 massive supervolcanic eruptions, and the last one of those, they went from 1.2 million years ago to 75,000 years ago. So spread out over a really long time. And that produced 2,800 cubic kilometers of material during that time. So that is definitely a super volcano. The thing about these eruptions and why I'm talking about them is in relation to Mars is the effects they can have on the atmosphere and the climate in this region. Now, I could take a smaller eruption, and this was Krakatoa in 1883. And this actually inspired Edvard Munch's The Scream, because he was out walking, I think it was 6 months to a year after the Krakatoa eruption. And he was, amazed by these beautiful red skies, but actually was found them kind of ominous to look at, and that's what kind of inspired this work of art. And that was all due to that eruption the year before, where all the material that was released during the Krakatoa eruption, which was not even a supervolcano, just a very large eruption, changed the skies throughout the whole of the world. And so we've got to think back to Mars. If we had a number of these supervolcanoes going off, was that something that meant that life had, maybe it started, or we know that Mars was a water world back billions of years ago, but it's no longer. We don't exactly know why it changed, and it could be that these supervolcanic eruptions actually changed the course of Mars's history. If there were enough of them that went off at the right time, it could have lost its atmosphere and changed the course of that planet. I like to talk about Io. I know that Io is the picture you had on the advert for this talk, and it's actually one of my favorite. I think it's probably my favorite moon because it's kind of like an early Earth. Io is one of the moons of Jupiter. It's the same mass and size as our moon, and as I said earlier, it therefore should be dead. We honestly didn't expect it to be quite so active, but obviously we went there and found out that it's got huge amounts of volcanoes on its surface, and they're very, very explosive, and they produce plumes plumes, and they, we've got this beautiful image here, or a GIF image showing how one of the volcanoes is actually erupting into space continuously. It's just crazy how we didn't know anything about this world before, the Voyager missions. We just had no idea it was going to be explosive like this. And that's because it just shouldn't be. It's small, but because it's sat next to the massive giant of Jupiter means that it can be active. And I love watching location. And I always think back to this. It's kind of like it's where, location is so important in the solar system as well. If you took Io, and gave it to Earth and let it, orbit around the Earth, then it wouldn't be active. The fact that it's around Jupiter means that it's pushed and pulled and tugged by the huge gravity of this huge planet. And the insides of Io are squashed and squeezed. And the rock that it's inside, which is inside Io, it is ground up against all the other rock. And that basically creates friction melting, which produces molten rock, which rises to the surface and makes volcanoes. So again, if you took Io somewhere else, it just wouldn't be active. But the fact it's next to Jupiter means it will forever be active as long as it's there, and it's going to continue to be a very exciting world. It's also very hot. It's as hot as Earth was before life started. So we can use Io to understand more about where we came from. I'm going to see how I'm doing for time. I'm probably speaking far too long. I'll try and get through a few ice worlds to cool us down before a few questions. And so I'll just start with Triton, which is the first icy world that we sort of discovered was volcanically active. And so it's got these cryovolcanoes. Again, Triton should be cold and dead. It is cold, but it's definitely not dead. One of the reasons Triton is an active world is because it's a captured moon. So a little bit like Io, it's kind of in this toing and froing around Neptune. It's sometimes a bit closer, sometimes a bit further away, because it was captured from the Kuiper belt out where Pluto lives now. And so it's not quite in a nice clean orbit at the moment, meaning that it's sometimes the gravity of Neptune kind of pulls on its insides. But you don't need much heat to be created to make something happen on an icy world, because if you've just got some water ice and you add some ammonia to it, you can actually make things flow at way different temperatures to what you'd need on Earth. And you don't need to melt rock. You don't need temperatures of 1,000 degrees Celsius to make cryovolcanoes. You just need a little bit of a temperature change to make things flow. And what we see across Triton is hardly any craters. We've got all these amazingly different terrains. You've got this cantaloupe terrain, which is meant to look like a cantaloupe melon. I don't really think it does look like it's a cantaloupe melon that much, but anyway, that's what it's been called. These are what we call diapirs of ice rising up, that we show we've got flow, we've got things moving underneath the surface that are more buoyant, that want to rise up. So it's an active world, and it's just very cold. Two of my favorite worlds, again, Europa and Enceladus. I've grouped them here rather maybe confusingly, but these are two different worlds. We've got Europa around Jupiter, Enceladus around Saturn. I group them because they show pretty much the same activity. They're icy worlds, but underneath their icy crust, they have oceans of salty liquid water, which we've been able to deduce from various means of studying them with spacecraft. The image on the top left shows Europa next to Earth, and it shows you the amount of water in Europa's salty ocean compared to the water in all of Earth's oceans. Now, it may be much smaller than Earth, but it's got a huge amount of liquid water. And what did I say earlier? Well, we think that liquid water is quite important on our planet. It makes us unique. But actually, maybe we don't need liquid water at the surface for life. And what's happening at Europa and Enceladus is that we think they have rocky cores that produce heat, that keep their mantles of ocean warm and molten, or liquid, if you want to call it that, if we're talking about ice. And they produce activity at the surface, but they may also produce a life-giving environment right down at the base of that ocean, a bit like we find at the base of our own oceans. We might have hot rock rising, and we might be heating a salty liquid that can create chemical processes that can support life at the base of those oceans. Now, one of the really cool things about Enceladus is that these plumes shoot out at kind of 800 miles per hour. It's quite hard to imagine that's what's happening again. It's this tidal heating that's happening as these moons orbit their planets. And actually, Enceladus's plumes supply Saturn's E-ring. So it's all made of ice from a volcano, which is, it's a dynamic environment. I think we often think of these worlds as, just existing, but actually what we need to think about is that they're still doing something. They're still forming. They're evolving in time, and I think we've got a lot more to discover about these. And there's some missions going back to Europa in the next decade, so we will be learning a lot more. And hopefully, I honestly think we might find something to do with life there, which would be really exciting. I can't complete a talk about space volcanoes without talking about Pluto. I can't, Pluto, well, Pluto was a planet when I was at school, as I'm sure most of us on this talk it was. But it's no longer a planet, obviously. But I love the fact that, NASA went out with their New Horizons mission just after we demoted Pluto to a dwarf planet. And then we discovered that actually it's one of the most exciting places in the solar system. It's definitely an active world. It's icy, it's cold, but what we see across its surface is that there's a lot going on. The image on the right here, we've got these convection cells of ice. So like we would see kind of in plate tectonics, you've got material rising up from the center of the planet, cooling at the surface and going back down. That's what happens within our mantle, and that sort of helps to move things around at the surface. We're seeing the same on Pluto, but within the ice. So again, like I said, if we've got icy worlds, you don't have to heat them up very much to create activity. And it also depends on what that world is made of. It's not all water ice. You might have nitrogen ice. You've got nitrogen glaciers on Pluto, and you might have ammonia and things that melt at different temperatures. There's ammonia on the surface of Pluto, which might not be very exciting, but once you learn that actually ammonia is broken down on quite short timescales by radiation, what we know about that ammonia being on the surface means that it's been replaced quite frequently and recently, because otherwise it would be lost to space. So we know that the inside of Pluto is active and literally giving out that ammonia onto the surface. We only did a flyby of Pluto in one of its moons, Charon, and Charon also, even smaller than Pluto, also shows many of the same features. We don't understand why they're active. We've got no explanation at the moment, really. I mean, there's lots of ideas, but we don't really know why they're active. They're not close to a large planet that could be producing tidal heating. They're too small to have primordial heat or radioactive heat left within them. So there's lots of ideas about how they possibly could still be warm enough to produce activity, but they are. They literally are, and they're not cratered surfaces. We need to go back to Pluto, but it's a very long way away, and I don't think we're going to be having a mission anytime soon. But luckily, we've got a lot of images to look at in the meantime. So in summary, I'll end here and just say, I think, there's volcanic activity everywhere across the solar system. I think Earth is the weird one in that, we have a lot of variation in the way that our volcanoes are produced. And they're all hot volcanoes, but actually when we go out across the solar system, mantle plumes seem to be the main way that we produce volcanoes. And there seems to be just as many cryovolcanoes as there are and hot worlds. Now, the potential for life, as I've mentioned, is quite high. I'm gonna say that, and I think probably the icy worlds have a higher potential for life than the hot worlds out there, mostly because the inner solar system worlds tend to be the hot ones, and they are mostly dead, but who knows what we're going to find at Venus in the next decade. So I think Europa and Enceladus in particular are the places to look, but also Titan might be an interesting place to look for life in the future. The main thing is that we really haven't studied these worlds in enough detail yet. The Voyager missions on the most part are the only way we've looked at some of these places. We need to get back, and scientists are always proposing missions to these places. We need to get back. There's not enough money, but luckily we're doing what we can as we go. And I'm just so excited. I just can't wait to see what we find out in the rest of my lifetime. But yeah, there's much to learn. So that's it. You can learn a lot more in my book, Fire and Ice. But yes, I will happily take some questions now if there are any.
Natalie, thank you very much. That was an absolutely fascinating talk. I know we've got about 40 or so members joining us on Zoom, and I think we've over 145 or 146 people watching on YouTube. So I'm sure there's many questions for you, but I thought I'd kick off myself and with something you said twice now, and it just struck me, and I thought it never occurred to me before. You said perhaps Earth is the odd one out here in terms of planetary dynamics. And given that volcanology is a relatively mature science on Earth, and as you were saying, we thought we knew what we would find out there, and we've been quite surprised. I'm just wondering, how much has volcanologists have to go back to school again when you're confronted with things like cryovolcanoes, and how useful is Earth, our understanding of volcanoes on Earth with tectonics and primordial heat? How useful of that a tool is it to use volcanoes to tell us what the internal dynamics, the internal geology of other worlds is now, or are we going to have to really start a whole new science when we do more exploration of these worlds?
Yeah, it's a bit of both. So particularly for rocky, hot volcanoes, we can use a lot of our knowledge from Earth to learn about those out in space. But we can also use them to learn about Earth, because they're often simpler systems. So if we take Io, for example, there's not plate tectonics, so we can use it as a way to study what we think Earth was like, 4 billion years ago, because it's just that simple system, and it hasn't evolved from that stage yet. So Earth is so complicated, and obviously to unpick our history, because we've had plate tectonics, is extremely hard to do. We've got so much going on here that trying to trace our history back in time is very, very hard. But we have a little bit of our history represented somewhere. Every bit of history is somewhere on our planet, almost. So we can use it both ways, but that's where, the field of comparative planetology comes in. We need to study our own planet with satellite in the way that we study other planets by satellite, because we've hardly been to any other planets in terms of, Mars. We've been with a lot of rovers, and you can do very detailed work in a very small area. But in terms of getting that planet overview, we need to use satellite data and then comparing it to what we see on Earth. Now, that's fine until you come to the icy worlds. And then, everything is different. The chemicals are different. The way that everything works because of the temperatures and the different pressures means that it's very hard to compare that to what we have on Earth. So what we then do, scientists are working on modeling, and they literally will use chambers to create those conditions on Earth, and they'll look, at how a icy lava flow might flow, but looking at it in a laboratory environment to try and understand if things would bubble, if they're cold, or if they, what might happen at the different pressures and how far lava flows can go. Because when we look at features, it's really hard for us to predict kind of what's happened or what that thing's made of, because we haven't even been there and measured the composition of the materials. So there's so many unknowns, and I think in most cases out in the outer solar system, we have such limited information. We get some chemical information usually when we do satellite, we do orbiter work or flybys. We usually have some kind of chemical information, but it's very broad. We don't get that real detailed knowledge. So yeah, a lot of it is like, in terms of the volcanoes, scientists really did have to rethink what is a volcano. And I cover that in my book, because we had this idea based on Earth, and it was a very Earth-centric view. And then suddenly, we're out in space, and volcanoes don't necessarily look like they do on Earth. So we need to rethink, what is a volcano? Does it need to be hot?
Exactly. Okay. Yeah. I hope we get a chance to get some material back at some point from some of these volcanoes, so you can study them. Peter, do we have questions online?
Well, I have a question. Basically, I was wondering if any of the missions that are planned are intended to do a proper fly through the plumes to actually analyze them.
Yeah, so now obviously it's happened with Enceladus, but it was sort of by accident. So the mission, it wasn't designed to sort of taste the plume, but then they discovered the plume was there, and they thought, well, our instruments can figure out what's in it. Now, the problem with the Cassini mission, there was no problems with it, I should say. The Cassini mission is amazing, but one of the issues was that they didn't know the plume was going to be there, so they didn't plan an instrument that was designed to measure what was in that plume. If we'd known it was going to be there, they probably would have put on, tested for organic material. They might have looked for amino acids within that plume. So what we could detect within it was that it's icy, and it contains these silica nanograins or granules. So what we know already is that those silica nanoglobules, whatever they're called, come from the very base of that ocean, where the hot rock of the core interacts with the base of Enceladus's ocean. And we get those same silica grains from our own oceans. So we know that there's this environment where you've got a lot of activity happening at the base of the ocean, and it's getting through the ocean and being shot out in a plume. Now, there's every expectation now, I think, from a lot of scientists, that there's probably also organic material within those plumes. Now, that doesn't necessarily mean life, but it could mean life. But we think there probably are organic grains within there. But unfortunately, the Cassini mission wasn't, designed to test for that. So I think when they go back, and particularly they'll be able to do this with Europa, they're going to be, detecting more chemicals within those plumes and finding out more about what's going on within that ocean, and particularly at the base of those oceans with those, black smokers or whatever they are at the base. So yes, they're definitely going to be going back to do that. Okay,
now we have one from Graham. He's asking if there's any evidence of volcanoes of any type on exoplanets.
So we haven't seen a volcano yet, but we do. There has been a planet detected that's probably hot and is probably volcanic, but we don't have kind of that resolution at the moment. So it's more based on the fact of where it is in relation to its star, and it is a hot planet, and it's probably a bit like Io, but we haven't. We've not got that resolution, or what we can't see whether it's got a volcano itself, but. I mean, the fact that we have so many stars out there and so many exoplanets, there's every expectation that our solar system isn't weird, and that there's going to be volcanoes out all over the universe. So yes, I think, we will find that out one day.
Okay. Can I hand over to Will now? Is there anything from YouTube, Will?
Yep, excellent talk, Natalie. It was really enjoyed. There are lots of great comments on YouTube. Just to say, there are people watching from South Africa to the United States, Croatia, Greece, just
wow, okay,
European countries. So it's quite an international following tonight. Excellent. I'll start with a question myself, actually. After hearing about the plumes, which had obviously 800 miles per hour managed to sort of escape the escape velocity of the icy moon. Do you think it's possible that planets would have possibly have volcanoes which would erupt to give more escape velocity potential of material from volcanic eruptions? I think it'd be very difficult, but I just wonder what you think about that, rather than the sort of typical meteoritic impacts, which would cometary impacts, which would cause material to leave moons or planets.
Yeah, I mean, I think in relation to Enceladus, obviously you've got the material coming out of that plume and producing the E-ring of Saturn. So yeah, I think that, that's completely possible. But I think with Io, I don't think that's happening on Io, because the material's heavier. It's because it is rocky material that's coming out. So I guess it depends if you're looking at icy material or gases, and gases could obviously escape much more easily. But I think, if you're looking at rocky planets, it's going to be harder, or I call them all planets, or rocky worlds, I should say, if we're looking at moons. But so you meaning kind of it will kind of produce meteoritic material out in space from these worlds that then we might sample on Earth? Is that kind of what you meant?
Absolutely. I just wondered, I suppose there's a limitation to the larger a moon or a body is, the more gravity it has, so the harder it is for something to escape. And but it's it's really amazing.
Yeah, I think the problem then is that it would be kind of trying to detect that material. So sure, it might be that we have a lot of cometary dust covering the surface of our planet, but we don't see it because it's so small. So then you think, well, what's the size of that material that's being blown out of that volcano if it did get into space, and then we orbit through that region where it's ended up? Would we be able to detect it? And this is that, the big problem with meteorites is that we know we've got meteorites from Mars and we've got meteorites from the moon. But because we haven't been to any of the other planets and sampled them directly, trying to prove that we have a meteorite from Mercury is impossible at the moment. We don't think we have any. And, a meteorite from Venus, well, we should have, right? We should have samples of those as meteorites on Earth, but we haven't been there to sample the rocks directly to make that comparison. So who knows? Yeah, we could have pieces of dust from a volcano in the solar system on our planet, but it would be very hard to know at the moment.
Excellent. And then we've got one question, which is may be able to answer. It's just from Din Utris. Just interested, sort of typically, how many sort of active volcanoes are there on Earth? Is it quite, because there's loads and loads of volcanoes, but how many sort of typically are there active?
So it depends, it depends how you class active. But if you're wanting, within any 1 year, there's probably 50 to 100 volcanic eruptions a year. Most of them don't make the news because, they're relatively small, they don't affect anybody. Obviously it's the bigger ones that affect communities or are more explosive or more, impactful. But often with, the ring of fire, let's call it, blame it on the sun and the Daily Mail again, but the ring of fire is often demonized slightly. But what happens is that we might get a really large eruption around the Pacific Ring at some point, and then the media pick that up, and it can obviously be quite devastating in one region. But then any eruption in that region that happens after that, which is completely normal and they happen all the time anyway, the media then sort of jump on all those events nearby and go, oh my goodness, the ring of fire is going to kill everybody, and it's going off. But one volcano erupting on the ring of fire doesn't trigger any other volcano in that system, because it's too complex, they're not related in that way. So yeah, I think I don't know, there are a lot of volcanoes happening all the time, but we just don't hear about most of them. But we hear, I think because last year, was it September, we had La Palma and Iceland go off within 1 month, didn't we? And that's actually the month my book came out, which was brilliant. I thought the earth was celebrating with me.
That's great. And just one final one from Karen Martin, who asked, saying that it's very interesting about the glassy beads found on the moon. And is that quite a rare thing, do you think, or is it just a chance find, or should there be loads more of these?
Oh no, there's actually more. Yeah, there's more on the moon. So I think there's lots of different colours as well, and the colours are dependent on the mineral, the element that is the main element within that volcanic rock that erupted. So you can get kind of green ones and different colours, but no, they're quite common. So yeah, fiery eruptions, fire fountain eruptions on the moon were quite a common event 3.5 billion years ago. So it was, quite an exciting place back then.
Excellent. Thanks very much. But it's very well enjoyed from YouTube. Thank you.
Thank you.
Right. Actually, I'm going to take the opportunity to ask a slightly more lighthearted question, and that was, if we're concluding, if the society could give you an unlimited budget for one planetary mission that you would get to choose, what would be your top pick at the moment as a volcanologist in terms of picking one mission in the solar system to really go and study and collect material and bring it back?
I always get asked this question actually, but I usually answer Io. But I think today I'm feeling a bit more excited. So I think it will be Titan today. I feel, we are going back with a mission called Dragonfly, and it's a rotorcraft that they're going to be sending on different sorties around Titan. And I think, it's a methane world. It's basically got a water cycle, but it's made of methane. So it has clouds, it has rainstorms of sorts, and they think it even has kind of thunder and lightning happening. There's lakes across the surface made of hydrocarbons, but there's every chance, there's liquid on the surface, it's just not liquid water. So it's almost like the most Earth-like place, and it's thought to be cryovolcanoes that are producing a lot of the activity and creating that environment. So I think it's going to be a really exciting place to investigate, and I hope that mission works out, because they're going to be able to kind of investigate a bit more than we would with just a rover, which obviously we have to be very careful with rovers, we don't break them, but with a rotorcraft you'll be able to see a lot more of the environment. So I would jump on that bandwagon and go out and just do more there and go and sample some of those lakes and see what we could find in them.
Well, I hope you get the opportunity to do so. It sounds like an absolutely fascinating thing to do as a career. Colleagues, can we unmute and thank Natalie for an absolutely wonderful presentation tonight? And I'm sure if people are interested in Natalie's book and publications, as I said, some of them are on our own on our own website. We've put some information up there. But Natalie, if someone wants to find more about your publications, where should they go?
My website or Twitter. So I'm at Starkey Stardust on Twitter, or my website is nataliestarkey.com. Wonderful.
Thanks very much. Well, thanks to all of our members and for everyone on YouTube for joining us this evening. We've really enjoyed listening to a wonderful presentation. Just a quick reminder that our next meeting is on Friday, the 1st of July. That'll be a hybrid meeting, so there'll be some of us in person at the Augustinian Hall in Edinburgh, and more of you online, and that'll be a members evening. So we look forward to seeing you then, and if in the meantime, look up and learn more about astrovolcanoes.